Hello and welcome back to this course, covering the exam topics for the JNCIS ENT certification. In this section of the course, we're reviewing BGP, concepts, configuration, and monitoring in Junos. In this lesson, we'll be covering an overview of BGP, or Border Gateway Protocol. Most network administrators and engineers are familiar with interior gateway protocols like OSPF, ISIS, and EIGRP, though far fewer have experience with an exterior gateway protocol like BGP. BGP is a special protocol, sometimes referred to as the routing protocol of the Internet. It's designed as an exterior gateway protocol, intended to be used to exchange routing information between entire autonomous systems rather than individual routers. Where IGPs, or interior gateway protocols, distribute routing information within an AS, BGP is intended to control the distribution of routing information between autonomous systems, which are potentially controlled by completely separate companies or administrative domains. So, let's jump in and review some of the features and characteristics of BGP. As I mentioned earlier, BGP is sometimes called the routing protocol of the Internet. This is because the routing protocol used ubiquitously by all major network transport service providers of the Internet is BGP. Whenever one AS needs to exchange routing information with another AS, BGP is almost always used. That said, although BGP is commonly used as an exterior gateway protocol, it can and is also often used as an interior gateway protocol as well. However, for reasons that we'll get to a little later in this lesson, when BGP is used as an IGP, it usually is implemented in conjunction with another IGP, like OSPF or IS to IS. With BGP extensions that allow carrying of VPN reachability information, BGP is often used as an interior gateway protocol in network service provider environments and large enterprise environments. Moving down further, we learned in our JNCIA and JNCIS studies that routing protocols are generally clumped into two main categories: link state and distance vector. BGP is often said to be in a class of its own, being a path vector protocol. In a later lesson, we'll cover the attributes used by BGP for path selection. However, none of them involve some cost or bandwidth-based metric by BGP itself. It uses attributes and the path of autonomous systems that the routing information has traversed. Referring to our diagram here, when BGP performs path selection, it essentially sees an AS as a single unit or cloud, like we have here. Even though these autonomous systems may actually contain thousands of routers communicating with an IGP, BGP simply sees it as a single autonomous system. Now, as you may have started to catch on, BGP is highly scalable, with the ability to reliably handle and exchange the entire Internet routing table. OSPF's underlying algorithm, for example, the Dijkstra algorithm, has a time complexity that is simplified to being exponential with the number of nodes or routers present in the area, meaning the time required to run the algorithm to calculate the best path to every destination increases exponentially with the number of destinations available. BGP is much more scalable with regards to processing the number of routes in the full public Internet IPv4 table. As of July 2023, the number of routes in the public Internet IPv4 routing table tops 920,000 routes, though BGP is capable of handling far more. BGP is most recently defined in RFC 4271, which supersedes RFC 1771. And finally, an important note that really differentiates BGP from other dynamic routing protocols is that it uses TCP as the transport protocol. Specifically, it listens over the well-known TCP port 179. TCP fundamentally provides reliable communication between nodes. So, now that we've reviewed an overview of BGP, let's take a look at some of the reasons why an enterprise network environment would implement BGP. An enterprise network environment will typically implement BGP at the edge when peering with their internet providers. However, when using a single ISP or internet service provider, it's typically not necessary to peer with the provider using BGP. Since a single provider is used, static routing, perhaps with route tracking or a qualified next hop, will be used to provide redundancy. Typically, BGP is not necessary in these circumstances. When using a single ISP, the ISP will typically allocate a public IPv4 subnet to the enterprise, which is non-portable. This means the public IPv4 subnet that is allocated to the enterprise cannot be advertised through any other ISPs without permission from the ISP that owns the subnet. Several regional Internet number registries exist in the world which control IPv4 subnet allocations. In the United States, ARIN, or the American Registry of Internet Numbers, controls the allocations of public IPv4 subnets to organizations. If an enterprise wants to have their own public subnet that they are able to advertise to multiple ISPs without needing permission from anyone else, then they'll need to purchase an IPv4 allocation from an Internet number registry. This is sometimes called a portable subnet, one which the enterprise has registered or purchased and belongs to the enterprise. The enterprise has the right to advertise the subnet out of multiple ISPs if they wish. BGP is used because it provides the maximum policy-based flexibility to influence both ingress and egress traffic flows for a particular autonomous system. Using the attributes available for BGP, one can influence how the inbound traffic flows into the enterprise. Now, we've mentioned a few times that BGP can be used as an EGP or an IGP. Let's now explore the differences between those use cases. When BGP is used as an external gateway protocol, it is referenced as external BGP, or eBGP. And when used internally, it's iBGP, or interior BGP. An external BGP peering occurs when two peers are in different autonomous systems. As we see in our diagram to the right, the link in the middle represents an eBGP peering, as it's between the routers in AS100 and AS200. This is the most common form of BGP peering in enterprise environments, and typically occurs with a network service provider. What defines an iBGP peering, though, is when the autonomous system numbers of the two routers peering together are the same. That is the only differentiating configuration between eBGP and iBGP. One of the important differences in functionality, though, is that eBGP messages have a TTL of 1 by default. This means the protocol is expecting its peer to be directly connected and to be peering with the interface IP address of the directly connected peer. If the eBGP peer is more than one hop away, then a feature called multi-hop must be configured to increase the TTL of the messages and allow them to traverse layer 3 hops. This is why eBGP peerings are typically done between interface IPs. iBGP peerings, on the other hand, are typically established between loopback interfaces to ensure highly available connectivity. Let's now take a look at the routing loop prevention mechanisms built into the BGP protocol and how they differ between iBGP and eBGP. Recall that eBGP exchanges routing information between autonomous systems, and this routing information can potentially traverse many autonomous systems. As routing information passes from autonomous system to autonomous system, the list of ASs that the route has passed through is included as an attribute of the routing information. If a receiving router sees its own AS number in the list of ASs that the route has traversed, the route is ignored. This is how eBGP prevents routing loops. As for iBGP, since these peerings are within a single autonomous system, using the AS path as a routing loop indicator doesn't make sense. For iBGP to prevent routing loops, it will not advertise a route learned from an iBGP peer to another iBGP peer. This means that routing information propagation will only propagate a single hop, essentially only to the device's immediate peer. Because of this, to ensure full connectivity, every iBGP-speaking router in an organization must have a direct peering with every other iBGP-speaking router. This is called the full mesh requirement for iBGP. As you can imagine, once an organization gets past a handful of iBGP-speaking routers, this becomes impractical to manage. There are ways to scale BGP without having a full mesh of peerings. By using a feature called route reflection, or BGP confederations. However, these are well outside the scope of the JNCIS ENT. Finally, let's go over some properties about BGP peerings in general. Unlike interior gateway protocols, BGP does not have any dynamic neighbor discovery mechanism. Peers must be configured explicitly in the device configuration. As we've mentioned before, BGP operates over IP as the network layer protocol and uses TCP as the reliable transport protocol. Specifically, it listens for BGP messages over the well-known port TCP port 179. Since TCP has a reliable transmission mechanism built in, BGP does not need its own protocols for acknowledging receipt of information. Finally, just to refresh, iBGP peers are typically configured between loopback addresses of devices, which requires layer 3 connectivity between the loopback interfaces. Although this could be done with static routing, this is almost always performed with a dynamic interior gateway protocol. It is in this way that iBGP is often said to ride on top of an IGP. This concludes the BGP overview lesson. I hope that this lesson has been informative for you, and I would like to thank you for viewing.